Okay, so we are moving on here to applications of the equilibrium constant. Sort of now that we figure out what it stands for, and we've used it to predict equilibrium concentrations, what can we do? Like, what else can we do with it? And the first thing we're going to look at is this concept of Q versus K. Q is essentially the same thing as an equilibrium constant. Products of reactants, coefficients become exponents, but instead the numbers that you put in are not equilibrium concentrations. They are usually starting concentrations. And then you calculate Q, which is that same formula, but with starting concentrations, and figure out then what will the reaction do in order to get to the equilibrium constant, because we know reactions at equilibrium, they will settle at that equilibrium constant ratio of numbers. So you can see this diagram over here kind of shows us a little bit about what helps us understand that concept. Q is the reaction quotient, so it's going to be a number, no units, just like K. Products of reactants, coefficients become exponents. And then what we will do is we will compare those two. Sometimes Q sometimes Q is much greater than K. And if Q is much greater than K, think about what Q is, right? It's always products over reactants. So if this number, Q, is a large number, a number bigger than K, then how will it get down to K? That means the top is going to need to get smaller and the bottom is going to need to get bigger, because Q will overall have to decrease. So Q will have to decrease to reach K, which means that the reactants will get larger, the products will get smaller, which means the reaction will proceed in the opposite direction. It will proceed to the left. Okay, we'll proceed to the left. That left-hand facing reaction will happen more quickly than the right-hand facing reaction, and then eventually the reaction will settle at equilibrium. Another scenario is when the Q is much less than K, right? So think of when Q is less than K, it's going to be products over reactants. What needs to happen for that to become the equilibrium constant, to become that numerical value? The products are going to have to increase, which means Q will increase to reach K, which means the products will have to get larger, right? Reactants will get smaller. And so the reaction will proceed to the right. So that right-hand facing reaction will happen more quickly. And then, of course, the third scenario is when Q is equal to K, and that would mean it's already at equilibrium. The reactants and products those reactions will proceed at equal rates, because that's what equilibrium is. So this is a very common question. Which way will the reaction proceed? They'll give you some starting information and they'll give you K. So at 1000 Kelvin, the value of QP for the reaction, 2 sulfur trioxide gas decomposing into 2 sulfur dioxide and oxygen gas is 0.338. Calculate the value of QP and predict the reaction in which the reaction will proceed toward equilibrium if the initial partial pressures are, and they give us those 3 numbers. So the first thing we do is we write out the expression, and it's the same as we would do for the equilibrium constant. So we would say it was the pressure of the SO2 squared times the pressure of the O2 over the pressure of the SO3, and that will be squared also. So now we can just start plugging in our numbers. 0.41 squared, 2.5 over 0.16 squared. And that gives us 16.4. So that's Q, might be just with 2 significant figures, 16. Now, what does that mean? So if this is Q, this is the situation where Q is a lot bigger than K. This number will need to decrease in order to reach K. Well, how does that decrease? That means the reactants excuse me, the top is the products will need to decrease, the reactants will need to increase. So that means that the reaction will proceed to the left. That left-hand making reaction will need to happen quicker because we would need that bottom, the product, the reactant, the 2SO3 to increase and the SO2 and O2 to decrease.